try and share much about what challenges I had and how I overcame them, so that hopefully it will give you some direction towards your research. And when you come through challenges, and mind you, you will, you'll know what to do, hopefully. So I'll just share my screen. So I'll just tell you a little bit about myself to start with. So I, Cody said, I recently finished my candidature. And so after I finished, actually before I finished, I also worked as a research assistant in geospatial science, which was quite different from my area of research, but still got involved with that. And yeah, I learned a lot. So yeah, that's probably something you can take away. Yeah, like you can always challenge yourself. And even if you think that the research may not be like within your expertise, I think you should give it a go. You never know where it's going to take you. So the title of my presentation today is Additive Manufacturing and Characterization of High Performance Polymers for Space Applications, and the key challenges I faced during this process. So my name is Kaifur Rashed. I was supervised by Professor Stuart Bateman, Dr. Abdullah Kafi, and Dr. Rania Simons from CSIRO. So this was a RMIT and CSIRO collaborative project, and I also had the opportunity to collaborate with ANSTO. So that's one thing I can share about as well. So I myself formed the collaboration with ANSTO. Uh, so like when I was thinking about my research topic, my supervisor asked me, "What would you like to do?" And I said, I want to study how radiation affects polymers in space, because we are already using some of these polymers in space, but we don't know how durable these polymers will be in the space environment. There's not much literature out there. So then I myself, contacted ANSTO scientists, and so I had to articulate the value proposition of my research, and why this is important, and why should they care. So when you're trying to form collaborations, and I found that RMIT is very open to forming new collaborations and helping HDR students form new collaborations. So get yourself out there and make collaborations, and that's something that's going to help you beyond your PhD as well when you're looking for work, because a lot of the postdoctoral researchers and even in jobs in industry, they want to see that you've worked in collaborative projects with industry and other government organizations and other universities. So when you're doing that, it's very important to articulate what value it has for scientific literature and also for the organization. So if you're going to present at a conference or publish the work, so make sure you say that, because that's something that they would be interested in as well. And a part of this work has already been presented at a conference, which is Asia Pacific International Conference on Additive Manufacturing, which we held last year in Sydney. So a bit of a background about my research. So with the growing interest in space exploration, there will be an increased demand for small satellites such as CubeSats. But cost of launching CubeSats to low Earth orbit is still very expensive, costing around $20,000 per kilogram. So the structure of CubeSats were currently manufactured using aluminium, but polymer matrix composites will reduce mass and result in cost savings. And additive manufacturing can also help reduce mass by offering design topology optimization and reducing joints and fixtures. As we know, with additive manufacturing, we don't have a lot of constraints that you have in traditional manufacturing processes. So you can essentially design whatever you like, and you'll be able to manufacture that. And fused filament fabrication is a type of additive manufacturing which uses polymers, and which is already being used in space for in-space manufacturing as well. So that was one of my motivations as well, to develop some materials that can be used in space, so that when we are manufacturing in space, we have some polymers that can, survive the space conditions and provide radiation shielding. So when we're talking about space, space is a very challenging environment, especially for polymers, because in space you need excellent mechanical properties, because there's immense amount of vibrations when a spacecraft is taking off, and there's quasi-static loads as well when the spacecraft is on orbit, and so there's temperature fluctuations between minus 130 degrees centigrade to 120 degrees C. So the material needed to have low coefficient of thermal expansion. And also there's a requirement by NASA and European Space Agency to have low outgassing properties of polymers that are used in space. So what outgassing is basically like when polymers are exposed to a vacuum environment, they release some gases that can affect other components in space, and that can also cause plastic deformation within the polymer. So you want to minimize outgassing properties. And electrostatic dissipation is also something that's important, because there are charges that built up on the structure, which can get grounded onto the electronics and affect their performance. And there's other radiation as well. So there's UV radiation, which is UVB is 9 times higher than in lunar orbit than in Earth orbit. And also there's cosmic radiation. So which consists of 85% protons, 14% helium, and 1% HZE, or high energy, high charge particles. So even though these particles are only 1% of the spectrum, they can still cause significant damage to polymers because of their high penetration power. And that's why I wanted to study their effects on polymers. So I'll just talk briefly about what the fused filament fabrication process is. So you essentially have a spool of polymer that is fed into a extruder. So the extruder then melts the polymer and then builds the design part layer by layer, and the platform moves to allow for the subsequent layers to be printed. So within this process, there are a lot of process parameters that we can change. So there's air gap, there's raster angle, there's raster width, contour, and contour to raster gap. All these things can be customized within the slicing software, as we call it, and that can affect performance and mechanical properties of materials as well. And this is part of the study. I'll speak about that in briefly as well. This is part of the study that I did, where I optimized the properties of printed parts by changing the process parameters. And I also used a filament extruder because I developed my own material. So I had to mix additives with polymer and then extrude them to make a spool of filaments. So one particular project that I'm sharing with you today is the parameter significance study on tensile properties of PEC. So I printed PEC in two different build orientation. It was flat and on edge. I used two different infill pattern as well. So lines and gyroid. I used different raster angles, so 0 to 90 degree, and then 45 and minus 45. And I changed the number of contours as well. And then tested their tensile properties to understand how these parameters affect the tensile properties. So I used a predictive model to run my experiments. So since these are basically you're dealing with 4 different factors at 2 different levels. So if you do full factorial, it will take you at least 16 runs. But then I used a predictive model, so I could do it within 8 runs. And these are the results of the tensile tests. So as you can see, there's a significant amount of difference in elongation at break. So the purple bars are the elongation at break. So between, say, the first 4 batches, it's the elongation of break was pretty high. But in comparison, the last 4 batches, the elongation and break reduced significantly. So the last 4 were printed on edge. So we can see clearly that, when you're printing at edge, the elongation and break, so the material becomes more brittle. And so when you're printing flat, it's extremely more ductile. So we are speaking of a difference between 43% and about 4%, so which is significant. So in Young's modulus, although it did vary a little bit, but it's not a lot. So it's between 1.8 to about 2.2 gigapascals, which is not significant. So on the right here, you see the tensile test graphs between 2 of like the best one and the worst one. So best being the batch 4, which had the highest elongation at break, and the worst being batch 8, which has the least elongation at break. So you can see that the flat samples actually stretched significantly before it failed. So part of the research was basically understanding why this happens. So I performed some fractography analysis. So I took the failed samples and examined their cross section of the failure. Sorry, cross section of the what do you call it? Sorry, I'm losing words here. So when it fails, and I basically looked at the cross section under an ACM, and then you can see clearly in batch 3, which is the flat sample, the failure was mostly ductile, but then on batch 8, you can see the individual rasters, and you can see how it failed in a brittle manner. But then again, the question comes, why does that happen? So then I looked at crystallinity, because crystallinity is one of the reasons why this could happen. If there's significant difference between in crystallinity between the 2 batches, then that could cause differences in mechanical properties. So I looked at crystallinity, and as you can see, between batch 3 and batch 8, the percentage crystallinity, it doesn't vary significantly. It's between 2.9 to 1.1. So both are essentially mostly amorphous or pseudoamorphous. So we can rule out crystallinity. We can say that no, crystallinity did not cause this. So then it could have then been porosity. So that's what I looked at later. So I examined the porosity using micro-CT at RMMF. So in this flat samples, you can see the porosity was around 0.1%, which is significantly low for a custom build printer. But the ones on edge, it was 3.2%, which is significantly higher. So you have a lot more stress concentration points. And since the pores were mostly oval, so the representative images you see here are of pores. And on the edge sample, you can see like the pores are quite large and sort of oval, which is what you don't want, because oval pores can cause more stress concentrations and then cause a premature failure. And the reason why that happens is because since I used a printer which is custom built, it did not have a heated chamber. So I only had a heated bed. So, and as the flat samples were quite thin, they were close to the bed, so they were mostly like heated the whole time. But then the samples that were on edge, since they were quite tall, um, as the nozzle went, far from the bed, um, it it did not have as much heat, so there a thermal gradient developed, and that's what caused so many pores. And that can also cause like reduced interlayer lamination as well. So, as a summary of results from the tensile stress properties, determine the optimum process parameters to maximize tensile strength. And I found that build orientation was most significant parameter that affected the tensile properties, followed by number of contours. Numbers of contours were also important in determining the tensile properties. And as I said, the degree of crystallinity were similar, so variation in elongation at break was believed to be due to porosity. And I've published this work as well in the International Journal of Advanced Manufacturing Technology. So if you want more details, please do check it out. So the next project I'll talk about is, I essentially then tried to improve the properties of PEC using additives. So like I spoke about before, in space, you need a lot of properties that PEC alone does not have. So you need the electrostatic dissipation or electrical conductivity, which PEC doesn't have inherently. So we needed to add some additives. So we looked at graphene nanoplatelets, graphene oxide, and boron carbide. So graphene nanoplatelets are known to increase mechanical properties in other polymers, and it also improves creep and wear resistance. And graphene oxide um, provides radiation protection, and boron carbide also improves radiation shielding. It was tested with medium density polyethylene and polyaryl ethyl ketone. But I found that boron carbide was significantly challenging to work with, which I'll share with you in a second as well. So the way I manufacture the composites are, I use a twin screw extruder to mix. First, I mix the PEG pellets and the additives together, and then I fed them through a twin screw extruder, and then I used air cooling to cool. That's something I'll share. I'll share my experience with as well. So I used air cooling. So in literature, you'll see most polymers when they extruding polymers, they use water cooling, and that's what we tried before. But as soon as the polymer hit the water, there were a lot of pores, a lot of pores or like small bubbles within the polymer. So water cooling was not suitable for PEG, so we had to go for air cooling. So essentially, yeah, I did that, and the twin screw extruder was used mainly to give a good mix between the polymer and the additives, and then I pelletized that, and I used those pellets to test them. So I performed thermal analysis using DSC and TGA. I studied the rheology as well, because in additive manufacturing, rheology is very important. You need to know the viscosity, and you need to know that whatever composite you're manufacturing will be able to be printed as well. So that's where rheology comes in. And I also tested their mechanical properties, so to give us an idea of if we are improving their mechanical properties or not. So these are the rheology results. So first, I performed strain amplitude sweep test to determine the linear viscoelastic region, and then I applied shear between the elastic region to then determine the complex viscosity. So over here, you'll see neat PEG, and also a lot of the composites, the boron carbide composites, the graphene oxide. And I also used, commercially available filaments. I pelletized them, and I studied their rheology to basically develop a benchmark. So as you can see, the green one on top here, that's a CNT PEC, which shows a significant amount of shear thinning. And all the formulations that I developed were below CNT PEC, so we can automatically assume that they were all printable. But there's some issues here as well. So if you can see the neat PEC, which is the black square boxes, and then graphene oxide, which goes below the neat PEG. So graphene oxide essentially lubricated the polymer chains, and that's not something I expected, because that's well, like in literature, when other people use graphene oxide, they had good success, but for PEG, like graphene oxide reinforced PEG became extremely challenging to work with. So they lubricated the polymer chains, and then when I tried to print them, like it was it's as if you're using an ink pen, and it's spreading too much ink, so you don't have any control over where the polymer is going. So when you design something, it's not going to be accurate when it's printed. So that basically tells me that it's important to have backup plans in your research. So even if you see that something has high chances of success according to literature, it's important for you to think about backup plans and incorporate other uh, additives or other materials that you can work with in case one doesn't work. So this is essentially the filament extrusion process, and like I said, on the first trial, we had a lot of air bubbles within the filament, and on second trial, when we used air cooling, um, so that issue was solved. And I solved this problem mainly by taking opinions of experts, because in literature, like everyone suggested using water bath to cool the filaments, but then I talked to the scientists at CSIRO to come up with a plan so that we don't end up with bubbles, and then they suggested to use air cooling. So I performed TEM on the filaments as well. So I took a cross section and then analyzed them under TEM to study the dispersion and distribution of the additives within the polymer matrix. So graphene oxide shows good signs of intercalation, and so does graphene. But boron carbide, we could only get fragments, because since boron carbide was very hard, even though we used a diamond tip to slice the samples, but we couldn't get complete cross sections on the boron carbide reinforced PEG because of its hardness. So, and this is the commercial CNT PEG. So this one also, shows good distribution, but it also has um, agglomeration as well. So then I studied EDS to determine if there's any agglomeration of boron carbide, and I saw, yes, boron carbide was significantly agglomerated, and that caused issues with feeding as well. So when I fed them into the printer parts were starting to wear off very quickly because of the hardness of boron carbide again. So conscious of time here, I'm just running quickly through the slides. Yeah, so this work that I did on boron carbide, graphene oxide, and graphene reinforced composites has also been published in the International Journal of Advanced Manufacturing Technologies. So do check it out, and if you have any questions, do let me know as well. So the next bit that I'm going to share with you is heavy ion irradiation using accelerators at ANSTO. Like I spoke before, I formed this collaboration with ANSTO, and then we had to determine what fluence of radiation should we implement on these polymers. So for that, we had to do some simulation using SPENVIS. So this is something that's used by European Space Agency. So we determined like what sort of fluences of radiation are there at different locations in space. And then if you see the black dots here, these are the doses that I put in my material. So I chose something that's somewhere in between. It represents some of these locations in space to then understand the properties of uh, understand the variation of properties in polymer, if any. So to do that, I printed small samples and I exposed the samples to radiation, and then I studied their chemical properties using XPS, FTIR, and EDS. And I also performed nanoindentation to understand if there's any variation in mechanical properties. And then the plan was to basically, after that, coat the samples and examine under SEM, and so that we could understand the fracture behavior before and after exposure. Uh, but again, this plan failed as well. So after we did nanoindentation, I tried to look at the samples under SEM. But even though we put like significant amount of force, but we were not able to see any fracture surface because everything was within the elastic limit of the polymer. So we could not like study the fracture behavior. So as a summary, like I studied the fluence of ions using SPENVIS, like I said, and I used SRIM simulations as well to understand how deeply the ion beams are penetrated within the polymer. And since ion concentration of iron was very low, like it was not visible in most characterization techniques. Um, and also nanoindentation confirmed that there were minimal variation in mechanical properties due to the ion beams. So essentially, um, additively manufactured PEG shows potential to be used for structural applications in space. This work is also published in Polymer Testing Journal, so do check it out as well. And if you have any questions, do let me know. And that's it. I'll conclude here, and I'll leave it to you guys if you have any questions for me.
Hi, everybody. Yes, Tariq, do you have a
Yeah,
question?
hi. Can you hear me? Can you hear me, guys?
Yes, we can hear you.
Hi, Kaifur.
Uh,
Thanks for your presentation. I had a couple of questions. The first question is, have
sure.
you tested your all samples in a space environment as well? Like, have you simulate that space environment in the lab? Because in the third slide, you mentioned a lot of factors that can impact the material properties,
Right.
like the UV radiation was one of that.
Yep.
Like you,
So I'll just go back to the slide. So I haven't
yeah,
tested UV radiation. So here. Yep. So
yeah, yeah,
essentially, yeah, I did test temperature variation. So we have access to dynamic mechanical analysis, or DMA, in
yeah.
building
Because the
three.
properties you studied in your composites is to me is look like a more generalized one, you know. Because but if we are connecting those materials with the space application, so I'm more
Yep.
interested in a space environment testing as well. So yeah,
Yep. Yeah. So that's what I'm saying. So with dynamic mechanical analysis, you can simulate the like temperature fluctuations in space. So I tested between minus 100 degree to 150 degree,
yeah,
and we have access to that in building three.
yeah.
And I've also tested the cosmic radiation, so using the particle accelerators at ANSTO, like I spoke before. But yes, to come back to your question, so in with the composites, like yeah, we did not have the time. That was one of the plan as well to do, but we could only test neat PEC, and we did not test the composites under space environment because
So the
it,
space
like
environment, those factors will be highly important, like what you are doing with your mechanical testing, and that will substantially decrease the mechanical properties. So you have to consider those all factors. Okay, and in addition to that, because you use that with ENSTO, you
yep.
use that ion accelerator.
Right.
So I will say, have you studied, because you have a lightning strike impact as well on your material. And electromagnetics, that one you mentioned the electrostatics as well there. So
Distillation, yes.
have you studied the electrical or dielectric properties of your material as well?
No, no, that was not within the scope of the project.
Okay.
So yeah, yeah, I did not study that.
Mm-mm-mm.
Yep.
Yeah, so probably, yeah, okay. So yeah, you can discuss with me. I have few other ideas as well, what you can study on those materials. Yeah, thank you. Thank you
Okay.
very much. Yeah, yeah.
Yeah, no problem.
Mm.
Do we have any further questions? Yes, Robert.
Hey, nice presentation. I just wanted
Thank you.
to ask quickly, when you conducted porosity testing, what was that machine you mentioned, and was it in RMMF?
Yes, it's in RMMF. It's called micro CT or microcomputer tomography. Yeah, you can use that to study metals, polymers as well. Uh, yeah, so you can get in touch with Chaitali if you want to study porosity as well.
Okay, thank you very much.
Yep, no problem.
Does anyone have any further questions? No? All good, Robert. I think you have your hand up, but I'm assuming the question is done. Thank you so much, everyone. And of course, thank you, Kaifur. Your presentation was amazing. I'm really glad that we got some questions in at the end as well. I do recognize that we are going a little bit over time, but I just wanted to let everyone know that this session was recorded. So if you had any reason to go back and maybe listen again to the Q&A section or upon any of the slides will also be made available. Thank you so much, Kaifur. And thank you everyone for coming and watching. Do you want to say any final words or say goodbye?
Yeah, thank you everyone for attending. And yeah, it's if you have any questions at all, or if you want to discuss anything in detail, do get in touch with me.
All right. Well, we will have 12 more of these coming out in the next 12 months. So look out for that invite. And thank you so much for coming. Okay.
Bye.
Bye, guys.